Today I'd like to talk about how we should add package versioning to Go. I'm sure you're all familiar with GoGet. You're probably also familiar with the ways that it breaks. But let me show you a few examples just so that we're all on the same page. Suppose we have a fresh Go installation, and we want to write a program that imports D. We run gogetD. That looks up and downloads the latest version of D, which right now is 1.0. It builds, we're happy. Now suppose a few months later we need C. We run gogetC. That looks up and downloads the latest version of C, which is C 1.8. C imports D, but goget finds that it already has a downloaded copy of D, so it reuses that copy. Unfortunately, that copy is D 1.0, and C needs a feature or maybe a bug fix introduced in D 1.4. So C is broken because the dependency D is too old. Since the build failed, we try again with goget -u C. Unfortunately, an hour ago, D's author published 1.6, which turns out to break C. Because goget -u uses the latest version of every dependency, including D, C is still broken. And now the dependency D is too new. So those are the two ways that goget fails. Sometimes it uses dependencies that are too old, and sometimes it uses dependencies that are too new. What we really want in this case is that the version is exactly the version of D that C's author was using and tested against. But goget can't do that because it has no awareness of package versions at all. Go programmers have been asking for better handling of package versions for as long as we've had goget. Various tools have been written separate from the Go distribution to help making installing specific versions easier. But without agreeing on a single approach, we can't create other version-aware tools. For example, a version-aware GoDoc or a version-aware vulnerability checker. So it's time to add the concept of package versions directly to Go, both so that goget stops using code that's too old or too new, and also to allow other tools to become version-aware. In February, I published a sequence of blog posts proposing exactly how to add versions to Go, along with a prototype implementation in a command called vgo. The proposal introduces a new import path syntax called semantic import versioning, along with a new algorithm for selecting which versions to use in a build called minimal version selection. Now you might wonder, why not do what other languages do? Java has Maven, Node has NPM, Ruby has Bundler, Rust has Cargo. How is this not a solved problem? What's more, last year we introduced a new experimental tool called dep that implemented the general approach pioneered by Bundler and Cargo. Why is the proposal not use dep? The answer is that we learned from dep that this general approach includes some decisions that make software engineering more complex and more challenging. And having realized that, we want to make different decisions to make software engineering easier and simpler instead. Then the question becomes, what is software engineering? How is software engineering different from programming? I like the following definition, which I've borrowed and adapted from Titus Winters. Software engineering is what happens to programming when you add time and other programmers. Programming means getting a program working. You have a problem to solve, you write some Go code, you run it, you get your answer, and you're done. That's programming, and that's difficult enough by itself. But what if that code has to keep working day after day? What if 5 other programmers need to work on the code too? What if the code must adapt gracefully as requirements change? Well, then you start thinking about version control systems to track how the code changes over time and to coordinate with the other programmers. You add unit tests to make sure that the bugs you fix are not reintroduced over time, not by you 6 months from now, not by that new team member who's unfamiliar with the code. You think about modularity and design patterns to divide the program into parts that team members can work on mostly independently. You use tools to help you find bugs earlier. You look for ways to make programs as clear as possible so that bugs are less likely. You make sure that small changes can be tested quickly, even in large programs. You're doing all of this because your programming has turned into software engineering. Nearly all of Go's distinctive design decisions were motivated by concerns about software engineering. For example, most people think that we format Go code with gofumt to make code look nicer or to end debates among team members about program layout. And that's good, but the real reason for gofumt is that if an algorithm defines how Go source code is formatted, then programs like Go imports or Go rename or Go fix or many others can edit the source code more easily, and this helps you maintain the code over time. As another example, Go import paths are URLs. If the code said just import UUID, you'd have to ask which UUID package. You could search on godoc.org for UUID and you'd turn up dozens of packages. If instead the code says import this specific path, now it's clear which package we mean. Using URLs avoids ambiguity, and it also reuses an existing mechanism for giving out names. And this makes it simpler and easier to coordinate with other programmers. Continuing the example, Go import paths are written in source files. They're not in a separate build configuration file. This makes Go source files self-contained, which makes it easier to understand and modify and copy them. And all these decisions were made with the goal of simplifying software engineering. Versions are absolutely necessary for software engineering. They are how you explain, both to tools and to other programmers, which code to use, even though that code is changing over time. Versions are especially necessary in large-scale software engineering, where there are many other programmers, and the code has to keep working for a very long time. Now, when I say large-scale software engineering, some people think of programs at a large company like Google. But in many ways, Google is small. We have all our code in one place. We can find all uses of a given package. We can list all the programmers working on a given program. In contrast, consider open source development on the internet. The code is not all in one place. We can't find all the uses of a given package. We can't list all the programmers working on a given program. This is the setting where we most need good support for versioning to simplify software engineering. Today, I'm going to present 3 broad principles behind the changes from Depp's design to Vigo's design. And all of them are motivated by wanting to simplify software engineering. I call them the principles of compatibility, repeatability, and cooperation. And for each one, I will explain the principle, show how it led us to make a different decision in Vigo than in Depp, and then respond as fairly as I can to objections against making that change. The first principle is compatibility. The idea that in a program, the meaning of a name should not change over time. If a name meant one thing last year, it should mean the same thing this year and next year. For example, programmers are sometimes confused by a detail of strings.split. We all expect that splitting hello world produces 2 strings, hello and world. But if the input has leading or trailing or repeated spaces, then the result has extra empty strings in the return slice. Suppose we decide that it would be better overall to change the behavior of strings.split to omit these empty strings. Can we do that? No. We've given strings.split a specific meaning. The documentation and the implementation agree on that meaning. Programs depend on that meaning. And changing the meaning would break those programs. It would break the principle of compatibility. We can implement the new meaning. We just have to give it a new name. In fact, years ago, to solve this exact problem, we introduced strings.fields, which is tailored to space-separated fields and never returns empty strings. We didn't redefine strings.split because we were concerned about compatibility. Following the principle of compatibility simplifies software engineering because it lets you ignore time when you're trying to understand your programs. People don't have to think, well, this package was written in 2015, back when strings.split returned empty strings, but this other package was written last week, so it expects strings.split to leave them out. And not just people, tools don't have to worry about time either. For example, a refactoring tool can always move a call to strings.split from one package to another without worrying that it will change its meaning. The most important feature of Go 1 was the declaration of compatibility. We said that we would stop changing the meaning of names in the standard library so that programs working with Go 1.1 could be expected to continue working with Go 1.2 and so on. And that made it easy for users to plan to stay. They knew their programs wouldn't start breaking. What does compatibility have to do with versioning? I bring it up because the most popular approach to versioning today encourages incompatibility. Most programmers today expect a versioning tool to support semantic versioning. which is the name for a version syntax convention introduced about 10 years ago. Semantic versioning has the unfortunate effect of making incompatibility seem easy. Every semantic version takes the form vmajor.minor.patch, and if two versions have the same major number, then the later version is expected to be backwards compatible with the earlier version. But if two versions have different major numbers, they have no compatibility relationship. There's absolutely nothing we know about them. Semantic versioning seems to suggest it's okay to make incompatible changes to your packages. Tell your users by incrementing the major version number. Everything will be fine. But this is an empty promise. Incrementing the major version number is not enough. Everything is not fine. If strings.split has one meaning today and a different meaning tomorrow, reading your code is now software engineering, not programming, because you have to think about time. It gets worse. Suppose B is written to expect strings.split v1, and C is written to expect strings.split v2. That's fine if you build each one by itself. But what happens when your package A imports both B and C? If strings.split has to have one meaning, there's no way to build a working program. For the Vigo design, we realized that the principle of compatibility is absolutely essential to simplifying software engineering, and we must preserve it. We gave this old advice of ours a new name. We call it the import compatibility rule. The import compatibility rule is if an old package and a new package have the same import path, then the new package must be backwards compatible with the old package. But then what do we do with semantic versioning? If we still want to use semantic versioning, the import compatibility rule requires that different major versions, which by definition have no compatibility relationship, must use different import paths. The obvious way to do that is to put the major version in the import path. And we call this semantic import versioning. In the example on the screen, mything v2 identifies semantic version 2 of a particular module, which is our name for a group of packages. Version 1 was just mything with no explicit version number. But when you introduce v2 or later, you have to add the version after the module name. So version 2 is mything v2, version 3 will be mything v3, and so on. If the strings package were its own module, then we'd have strings and strings v2 with different split functions. And then our build works out fine because B says import strings and C says import strings v2, and those are different packages. It's okay to build both into the program, and now B and C can each have the split function that they expect. Because strings and strings v2 have different import paths, people and tools automatically understand that they name different packages, just as they already understand that cryptorand and mathrand are different. No one needs to learn a new concept for keeping packages separate. If we replace strings in this example with an arbitrary package D, then we have a classic diamond dependency problem. Both B and C build fine by themselves, but with different conflicting requirements for D. And then if we try to use both of them in a build of A, there's no single choice of D that works. We can't run our build. Semantic import versioning cuts out diamond dependencies. There's no such thing as conflicting requirements for D. D version 1.3 must be backwards compatible with D version 1.2 and so on. And D version 2 is a separate package, D/v2. Now, the most common objection to semantic import versioning is that people don't like seeing the major versions in the import paths. Of course, what this really means is that people are not used to seeing the major versions in the import paths. I mentioned earlier that Go import paths are full URLs in order to be precise about exactly which package is meant by an import. In the early days of Go, we didn't do that. You manually downloaded and installed the source code for some package named UUID, and then you just wrote import UUID. Changing to URLs for import paths eliminated this ambiguity and this manual step, and it made go-get possible. And people did complain at first, but now the longer paths are second nature to us. We rely on and we appreciate their precision because it makes software engineering simpler. I expect the same thing to happen with major versions and import paths. We'll get used to them, and we'll come to value the precision and the simplicity they bring us. Another common objection is that upgrading from, say, v2 of a module to v3 of a module requires changing all the import paths referring to that module, even if the client code doesn't need any other changes because the parts that it uses are not being broken in an incompatible way. This is true. It does require changing the import paths, but it's also easy to write a tool to do a global search and replace. We also intend to make it possible to handle these upgrades automatically with GoFix. And both of these objections implicitly suggest, well, we must have to keep the major version information somewhere else in a separate metadata file. If we do that, then an import path won't be precise enough to identify the semantics of the things in the package. And so all programmers and tools will have to look in the metadata file to answer the question, which version is this? What is the meaning here? Which strings.split am I calling? If instead we keep import paths semantically precise, then programmers and tools don't need to be taught a new way to keep different major versions of a package separate. Another benefit of having the major version in the import path is that when you are updating from v2 to v3 of a package, you can update your program gradually in stages, maybe one package at a time, and it's always clear from the import paths which code has been converted and which code has not. Another common objection is that having D version 1 and D version 2 in the same build should be disallowed entirely. Then D's author won't have to think about the complexities that arise from having two different versions in one program. For example, maybe package D defines a command line flag or registers an HTTP handler, so that building both versions would require some sort of explicit coordination between those versions. In fact, DEP enforces exactly this restriction. And some people say it's simpler, but this is simplicity only for D's author. It's not simplicity for D's users. And normally, we hope, users outnumber authors. If D version 1 and D version 2 cannot coexist in a single build, then the daemon dependencies are back. You can't convert a large program from D1 to D2 gradually, the way I just explained, package by package. And in internet scale projects, this will fragment the Go package ecosystem into unmixable sets of packages, those that use D1 and those that use D2. My blog post about semantic import versioning has a detailed example of this. Now, DEP was forced into this restriction for technical reasons. But Cargo and other systems don't impose this restriction, presumably because it makes it too hard to work on large programs. A final objection is that versions and import paths are unnecessary overhead when you're just starting to design a package, you have no users, and you're making frequent backwards incompatible changes. That's absolutely true. But semantic versioning has a special case for exactly that situation. In major version 0, there are no compatibility expectations at all. So you can iterate quickly when you're first starting out and not worry about compatibility. For example, version 0.3.4 doesn't need to be backwards compatible with anything else, not 0.3.3, not 0.0.1, not 1.0.0. And so semantic import versioning makes a similar exception. Major version 0 is not mentioned in the import paths, nor is major version 1. And in both the semantic versioning exception and the semantic import versioning exception, the rationale is that time has not entered the picture. You're not doing software engineering yet. You're just programming. But this does mean that if you use v0s of packages, then you are taking on the responsibility to update your code when new versions make incompatible changes. And the import paths won't keep them separate. The second principle is repeatability for program builds. And by repeatability, I mean that when you are building a specific version of a package, the build should decide which dependency versions to use in a way that's repeatable, that doesn't change over time. My build today should match your build tomorrow, and any other programmer's build next year. Most versioning systems don't make that guarantee. We saw earlier how GoGet doesn't provide repeatability. First, GoGet used a version of D that was too old, and then GoGet used a version of D that was too new. You might think, of course GoGet makes this mistake. It doesn't know anything about versions at all. But most other systems that do know about versions still make this mistake. And I'm going to use DEP as an example here, but Bundler and Cargo work the same way. DEP asks every package to include a metadata file called a manifest, which lists requirements for dependency versions. When dep downloads C, it reads C's manifest and learns that C needs D1.4 or later. And then dep downloads the newest version of D satisfying that constraint. Yesterday, that meant D1.5. Today, that means D1.6. The decision is time dependent. It changes from day to day. The build is not repeatable. Now, the developers of Bundler and Cargo and dep understood the importance of repeatability. So they introduced a second metadata file called a lock file. If C is a whole program, what Go calls package main, then the lock file lists the exact version to use for every dependency of C, and dep lets the lock file override the decisions it would normally make. Locking in those decisions ensures that they stop changing over time and makes the build repeatable. But lock files only apply to whole programs, to package main. What if C is a library being built as part of a larger program? A lock file that was meant for building just C might not satisfy whatever additional constraints are in the larger build. And so dep and the others ignore lock files associated with libraries and just fall back to their usual time-based decisions. So when you add C1.8 to a larger build, the exact packages you get along with it depend on what day it is. Dep starts with this time-based decision about which version of D to use, and then it adds a lock file to override that time-based decision for repeatability. Vigo, instead, makes a decision about which version of D to use in a way that doesn't change over time. And then it gets repeatability in all builds without any kind of lock file override. Vigo's algorithm works like this. Each package specifies a minimum version of each dependency. For example, B1.3 requests D1.3 or later, and C1.8 requests D1.4 or later. Vigo prefers to use those exact requested versions, not the later versions. If we're building B by itself, we use D1.3. If we're building C by itself, we use D1.4. If different parts of a build request different minimum versions, Vigo uses the latest requested version. So the build of A sees requests for D1.3 and D1.4, and it chooses D1.4. That decision does not change over time. It doesn't care whether D1.5 or D1.6 exist. I call this minimal version selection because for each package, it selects the minimum version that satisfies the requests, which is also the maximum of the requests. And also because it seems to be just about the simplest possible approach that could work. Now, minimal version selection provides repeatability for whole programs and for libraries, always without lock files, because it removes time from consideration. Every chosen version is always one of the versions mentioned explicitly by some package already chosen for the build. The usual first objection to prioritizing repeatability is to claim that preferring the latest version of a dependency is a feature, not a bug. The claim is that programmers either don't want to or are too lazy to update their dependencies regularly. So tools like dep should use the latest dependencies automatically. The argument is that the benefits of having the latest versions, as far as bugs fixed and security problems, outweigh the loss of repeatability. But this argument doesn't hold up. Systems like dep provide lock files, which then require programmers to update their dependencies by hand, exactly because repeatable builds are more important. When you deploy a one-line bug fix, you want to be sure that your bug fix is the only thing that's changing, not that you're also picking up different, newer versions of your dependencies. You want to delay upgrades until you ask for them so that you can be ready to run all your unit tests, all your integration tests, and maybe even production canaries before you start deploying that code to real production. Everyone agrees about this. Lock files exist because everyone agrees about this, because repeatability is more important than automatic upgrades. The more nuanced argument you could make against minimal version selection would be to admit that yes, repeatability matters for whole program builds, but then argue that for libraries the balance is different, and having the latest dependencies is more important in a library than having a repeatable build. I disagree with this. As programming increasingly means connecting large libraries together, and those large libraries are increasingly organized as collections of smaller libraries, all the reasons to prefer repeatability of whole program builds become just as important for library builds. The extreme limit of this trend is the recent move in cloud computing to so-called serverless hosting, like Google App Engine or Amazon Lambda or Microsoft Azure Functions or Google Cloud Functions. And in all those systems, the code we upload is always just a library, not a whole program. We certainly want the production builds on their servers to use the same versions of the dependencies as on our development machines. Of course, no matter what, it's important to make it easy for programmers to update their dependencies when they choose to. And so we have tools to report which versions of a package are in a given build or even a given binary, including reporting which packages have updates available, which packages have known security holes, and so on. The third principle is cooperation. We often talk about the Go community and the Go open source ecosystem. The words community and ecosystem emphasize that all our work is interconnected, that we're building on and depending on each other's contributions. The goal is one unified system that works as a coherent whole. The opposite, what we want to avoid, is an ecosystem that's fragmented, split into groups of packages that can't work with each other. The principle of cooperation is that we must all work together to keep the ecosystem healthy and thriving. If we don't, then no matter how technically sophisticated our tools are, the Go open source ecosystem is guaranteed to fail. The implication is that it's okay to rely on cooperation to fix incompatibilities. The tools don't have to do everything. For example, once again, we have our favorite package C1.8, which requires D1.4 or later. And thanks to repeatability, a build of C1.8 by itself will use D1.4. If we build C as part of some larger build that needs D1.5 for some other reason, that's fine. It will work. And then D1.6 is released. And some larger build, maybe continuous integration testing that forces the latest versions of all packages, discovers that C1.8 does not work with D1.6. What do we do now? The solution is for C's author and D's author to cooperate and release a fix. So maybe C depends on buggy behavior that was fixed in D1.6. Or maybe C depends on unspecified behavior that changed in D1.6. Then the solution is for C's author to release a new version, 1.9, that cooperates with the evolution of D that has happened. Or maybe D1.6 simply has a bug. Then the solution is for D's author to release a fixed D1.7, cooperating by respecting the principle of compatibility. Now take a minute to look at what just happened. The latest C and the latest D didn't work together. That introduced a small fracture in the Go package ecosystem. C's author or D's author worked to fix the bug, cooperating with each other and the rest of the ecosystem to repair the fracture. This cooperation is essential to keeping the ecosystem healthy. There is no adequate technical substitute. Vigo's repeatable builds mean that a buggy D1.6 won't be picked up until users explicitly ask to upgrade. And then when they upgrade and find out it doesn't work, they can undo the upgrade. That creates time for C's author and D's author to cooperate on a real solution. Vigo makes no other attempt to work around these temporary incompatibilities. In contrast, the DEP design, following Bundler and Cargo and most other systems, allows one package to document an incompatibility with another. So for example, when C's author finds out that C1.8 doesn't work with D1.6, DEP allows and encourages issuing a new version, C1.9. And C1.9 documents, it's the same code, but it documents that it needs D later than 1.4, but before 1.6. And the idea is that documenting the incompatibility helps DEP avoid it in future builds. Now in DEP, avoiding the incompatibility is important because as soon as D1.6 is released, all future fresh builds of C will use it and break. This is a build emergency. All of C's new users are broken. If D's author is unavailable, or C's author doesn't have time to find the right fix, the argument is that C's author must be able to take some step to protect users from the breakage. And that step is to release C1.9, documenting the incompatibility with D1.6. Then new builds of C will grab the latest one, C1.9, see that they can't use D1.6, and avoid the breakage. This emergency doesn't happen at all with Vigo, because Vigo has minimal version selection and repeatable builds. Using Vigo, the release of D16 does not affect C's users because nothing is explicitly requesting D16 yet. Users keep using the older versions of D that they already use, so there's no need to document the incompatibility because nothing is breaking. There's time to cooperate on a real fix. Now, looking at DEP's approach of documenting incompatibility again, releasing C19 is actually not a perfect solution. For one thing, the premise was that D's author created this build emergency by releasing D16 and then was unavailable to release a fix. So it was important to give C's author a way to fix things by releasing the new C19. But if D's author might be unavailable, what happens if C's author is unavailable too? C's author presumably didn't know D16 was coming out a minute ago. Then the emergency that's caused by these automatic upgrades continues, and all of C's new users stay broken. Vigo's repeatability avoids this emergency entirely. Also, suppose the bug is in D, and D's author issues a fixed D17. The workaround C19 says it needs a D before 16, and so it won't use the fixed D17. C's author has to go back and issue a new C110, that just to allow the use of the fixed D. And in contrast, if we're using Vigo, C's author doesn't have to issue C19 and doesn't have to undo it by issuing C110. So in this simple example, Vigo ends up working more smoothly for users than DEP. It avoids this build breakage automatically, which creates time for cooperation on the real fix. And ideally, C or D gets fixed before any of C's users even notice. But what about more complex examples? Maybe DEP's approach of documenting incompatibilities is better in more complicated situations. Or maybe it keeps things working even when the real fix takes a long time to arrive. Let's take a look. To do that, let's rewind the clock a little bit to before the buggy D16 is released. This slide shows the documented requirements for all the relevant package versions. It shows the way both DEP and Vigo would build the latest C and the latest A. DEP is using D15, and Vigo is using D14, but both tools have found working builds. Everyone is happy. Now suppose the buggy D16 is released. DEP builds pick up D16 automatically and break. Vigo builds keep using D14, and they keep working. This is the simple situation we were just looking at. Well, let's see if we can construct a more complicated situation that breaks Vigo. But first, wait, DEP's users are broken, and we need to fix that. So we release C19, which documents the incompatibility with D16. DEP builds start picking up C19 automatically, builds start working again, now we're happy. Vigo can't do this, but Vigo's builds also aren't broken, and our goal here is to break them. So let's see if we can do that. To that end, let's release a new B that requires D16. The plan is that after we have the B that requires the latest D, we can introduce a new A that requires the latest B, and that will force Vigo to use this combination that doesn't work, which will finally break the Vigo-based builds. But let's not get ahead of ourselves. We haven't done any of that yet. All we've done is release the new B, B14, which requires the new D, D16. Vigo builds are still unaffected, thanks to repeatability, but surprise, DEP builds of A pick up B14 automatically, and now they're broken again. What happened? It turns out DEP prefers to build A using the latest B and the latest C. But that's not possible. In this case, they don't agree on an acceptable version of D. The latest B wants D16, and the latest C wants D before 16. So DEP doesn't give up. It looks for some other combination of versions of B and C that do agree on an acceptable D. In this case, it decided to keep the latest B, which means it has to use D16, which means it can't use C19. And so if it can't use the latest C, then DEP tries older versions of C, and so it tries C18, and that looks okay. It says it needs D14 or later, and so D16 counts. So DEP uses it, and that breaks. The problem is that we know that C18 and D16 are incompatible, but DEP does not. It can't know, because C18 was released before D16. We couldn't predict the future that it was going to break. And all package management systems agree that package contents must be immutable once they're published, which means there's no way to retroactively document that C18 doesn't work with D16. Releasing C19 and hoping that DEP would use that instead was the best we could do. And because DEP prefers to use the latest version of a package, most of the time it will use C19 and know then to avoid D16. But if DEP can't use the latest of everything, it starts trying earlier versions of some things, including maybe C18. And using C18, it doesn't have the information that D16 is not okay. Even though we know better, it doesn't, and the build breaks. Or maybe not. Strictly speaking, DEP didn't have to make that decision. When it realized that it couldn't use both the latest B and the latest C, we assumed before that it kept the latest B. But if instead it kept the latest C, then it would realize it needs an older D, which would preclude using the latest B, so it would use an older B, and that would actually produce the working build on the right side of the slide. In effect, DEP would ignore that this new B existed. So maybe DEP's builds are broken, or maybe they're not, depending on the coin flips that it makes. But for the sake of DEP's users, let's assume that DEP made the right decision and the builds are working. After all, we're not trying to break DEP, we're trying to break Vigo. And we're finally ready to do that. Now we can release a new version of A, version 1.21, which requires the latest B, which in turn requires the latest D. And so now when Vigo builds that latest version of A, it's forced to use the latest version of B and the latest version of D. And in Vigo world, C19 doesn't exist because that's not expressible, so Vigo uses C18. And the combination of C18 and D16 does not work. And so finally, we've convinced Vigo to break the build. But look, the DEP builds are also using C18 and D16, so they're also broken. Now remember, on the last slide, DEP had to make a choice. It could use the latest B, or it could use the latest C. And if it chose the latest B, the build broke. And if it chose the latest C, the build worked. But this new requirement that we just added to A is forcing DEP to use the latest B. And that's the choice that leads to a broken build. And so DEP ends up breaking the build exactly like Vigo does in this example. So what should we conclude from all of this? First of all, documenting an incompatibility for DEP or Cargo or Bundler or all these other systems, I'm not picking on DEP, does not guarantee to avoid that incompatibility. Second, a repeatable build like in Vigo also does not guarantee to avoid the incompatibility. Both tools can end up building the incompatible pair of packages. But as we just saw, it takes multiple intentional steps to lead Vigo to the broken build, steps that lead DEP to the same broken build. But along the way, those steps broke DEP multiple times, including the first time when it broke all by itself from the automatic update and use of the buggy package. And Vigo's build didn't have those extra breakages along the way. So DEP is not really broken or misbehaving. The fundamental problem is the principle of cooperation. Tools cannot work around a lack of cooperation. There's really nothing it could do perfectly to avoid this situation. But when you run through these examples, it turns out that Vigo's not updating as aggressively avoids more situations and does it more easily. The real solution here for this C versus D incompatibility is to release the new fixed version of either C or D. Trying to avoid the compatibility is only useful insofar as it creates more time for C's author and D's author to cooperate on a fix. Compared to DEP's approach of preferring latest versions and documenting incompatibilities, Vigo's approach of repeatable builds and minimal version selection with no documented incompatibilities creates more time for cooperation with no build emergencies and no explicit work by users. And then we have time to rely on cooperation to produce the real fix. So those are the three principles of versioning in Go, the reasons that Vigo deviates from DEP's design and Cargo's and Bundler's and others. Compatibility, repeatability, cooperation. I said earlier that the principles were all motivated by software engineering, which is what happens to programming when you add time and other programmers. Compatibility eliminates the effects of time on the meaning of a program. Repeatability eliminates the effects of time on the result of a build. And cooperation is an explicit recognition that no matter how advanced our tools are, we do have to work with the other programmers. We can't we can't always and forever work around them. The three principles also reinforce each other in a virtuous cycle. Compatibility enables a new version selection algorithm, which provides repeatability. Repeatability makes sure that buggy new releases are ignored until they're explicitly requested, which creates more time to cooperate on fixes. And that cooperation, in turn, reestablishes compatibility, and the cycle goes around. So for more information about our approach to versioning, you can search the web for Go package versioning proposal. You'll find the official Go blog post, as well as more detailed posts on my own blog. And today, the plan is that Vigo-like functionality will be included as a kind of preview in the Go command in Go 1.11, with official support locked down in Go 1.12. The blog posts have detail about how to download and try Vigo today, even before Go 1.11, so please do that. Download it, try it, and let us know what works for you and what doesn't. Thank you very much.